In this problem, we're looking at a truss which is made up of members BD and CD. There's a vertical load which is acting at joint D. We know that the temperature of member 1, which has the thermal coefficient of expansion of alpha, is the temperature is changed by an amount of delta T, whereas member 2, the temperature remains unchanged. As a result of the axial load and the temperature change, what are the stresses in members 1 and 2? And what are the horizontal and vertical components of the displacement there of joint D? Let's do a little bit of trig first. If this length of 1 is L and the vertical height between C and B is H, then we could define this angle of phi, where phi is equal to the inverse, not tan, but it's the inverse sine of H over L. So that is our phi. We also need to define our member angles according to the conventions we have if we're going to use the elongation displacement equations, and we will. So let me define first x like this and y like that. So x like that, we go counterclockwise at the base. So theta 1, therefore, is equal to 360. Subtract away the angle of phi. So phi is the same angle as that. Where phi 2, again, we measure from the x-axis, counterclockwise sense, at the base, and we see that theta 2 is a 0. So also that length 2 is going to be equal to L times cosine of phi. So we have all the information that we need for those three angles that we're going to use, and also to be able to calculate the length of member 2. Let's look at equilibrium. I'm going to do a node equation for joint D. Applied force F. We have the member force there, F2. We have a member force of F1. Keep in mind that that is at an angle of phi. So when we sum forces in the x direction for joint D, I have minus F1 cosine phi minus F2 is equal to a 0. I sum forces in y. The y component gives me a plus F1 sine phi, and that's minus p. So from this, we see that the member force F1 is equal to the applied force P divided by the angle of phi, and therefore we have that F2 is equal to minus F1 cosine phi. So that's going to be minus P times cotangent of phi. So this problem, as far as determining the member forces, is determinate. We were able to get two equations for the two unknowns. And so therefore the axial forces, we have that sigma 1 is equal to F1 divided by A1, and sigma 2 is going to be now the known force F2 divided by A2, and the cross-sectional areas, the two members are the same. So strictly from equilibrium, we're able to get the internal stresses. Okay, so now what we want to do is find the horizontal and vertical components of displacement. So we have for our elongation equations, the elongation equations say that E1 is going to be equal to F1 L1 divided by E1 A1 plus alpha delta T. E2, that's going to be equal to F2 L2 divided by E2 A2 plus alpha delta T. Well, it says here that 2 doesn't change in temperature, So that's all that we have got. So we've got enough then to find E1 and E2. Therefore, our compatibility equations, our displacement equations, are our usual um, displacement elongation equations, which says that E1 is equal to the displacement there of joint D times cosine of theta 1. We've got that. The vertical displacement of that point D, sine theta 1. And E2 is equal to UD cosine theta 2 plus V sub D sine theta 2. So what we see is that since theta 2 is a 0, we know that cosine is going to be equal to 1, sine is going to be equal to a 0, so there's no distinction between the horizontal displacement of D and the elongation there of 2. And so since we have UD, we can say then that E1 plus E2 cosine theta 2 plus V sub D sine theta 1, and I apologize, this should be a cosine of theta 1, and from this we know what E1 and E2 are. Those are from the above equations. We know the angles. So it says here that the vertical component of displacement of D is going to be E1 minus E2 cosine of theta 1 divided by sine of theta 1. So this gives us V sub D, this gives us U sub D, and that. So as we look back at the problem, in terms of determining the load that's carried by the members of B, D, and CD, that was determinate. We were able to get the forces strictly from equilibrium, and that made life really easy because we could get the stresses, we could get the elongations, and the elongations then feed into our displacement equations from here. And that made it relatively simple then to find our vertical and horizontal components of displacement there of D.